Hello, it's time for a bunch of line integrals. So most of the ones we're going to be dealing with are in the form f.dr, or some expanded form where you will see a dx, dy, dz. It's really the same thing that we're doing every time. We want to parametrize a curve. In some case, they already have it parametrized for us. And then we need to take the r prime of that parametrization and dot it with f of r of t. So those are the general steps we're going to take every time. Let's see if we can go through these motions on this first one. So r of t, they say, is sine t, cosine t, t. So r prime of t is going to be negative, whoops, oh, that's wrong. It's going to be cosine t, negative sine t, 1. And now we just need our f of r of t. Well, f is, our x component is y up here, so that's going to be cosine t. And then we want negative x, so negative sine of t. And then we want xy for our z component, so that's going to be sine t cosine t. So we take this dot product, adding these guys together, we are going to end up with our integral on the bounds of t over here from 0 to pi of cosine squared t plus sine squared t plus sine t cosine t dt. And we know that this can simplify down to 1 over here. Okay, now we have an integral that we can evaluate. We know that sine t cosine t is 1/2 sine 2t. So this whole thing is going to work out to t minus 1/4 cosine 2t evaluated on 0 to pi. This is going to give us pi minus 1/4 times the cosine of 2t, so just minus 1/4. And by 2t I mean 2 pi. And over here we're going to get 0 minus 1/4 times the cosine of 0, which is 1. And so we evaluate everything and we are left with pi. Let's compute another f.dr line integral, except this time we have to parametrize it for ourselves. So whenever we're parametrizing y equals x squared, all we do is we set x equal to t, y to t squared, and then we can pull our bound straight from our x values here, because we know that since x is equal to t, our change in x will also be our change in t. So in this case, 0 is less than or equal to t, which is less than or equal to 1. And so our parametrization for r of t is going to be t squared, and r prime of t is going to be 1, 2t. And now all we need to do is set up our f of r of t, and our first component is just xy. So taking that from r of t, that's going to give us t cubed, and then x plus y, which is t plus t squared. So now dotting these guys and setting up our integral from 0 to 1, we get t cubed plus 2t squared plus 2t cubed dt, which is the same thing as the integral from 0 to 1 of 3t cubed plus 2t squared dt. We integrate this, we're going to get 3/4 t to the 4th plus 2/3 t cubed on 0 to 1, and this evaluates to 3/4 plus 2/3. We can put this into 12ths to add everything together. We are going to get 9/12 plus, what would this be, times 4 plus 8/12. And that gives us our answer, which is 17/12. Let's find the work done by this force field on a particle moving along the parabola y equals x squared from the point 1, 1 to the point 2, 4. Well, we just did this parametrization before. We can do it again. We know that x is equal to t, y is equal to t squared, and our bounds on t are just our values for x. So 1 is less than or equal to t, which is less than or equal to 2. We also know that what we're computing when we do the integral over c of f dot dr, really what we're finding is the work done on something moving along the path c by the force field F. So we can just set this up and in our normal way, and we should be able to figure things out. So we know that our r of t is t squared, and r prime of t is 1, comma 2t. Now let's make our f of r of t, which is going to give us, whoops, gotta turn off Wi-Fi. There we go. Our f of r of t, we're going to get 2x sine y as our first component, where x is t, so 2t sine of t squared. And then our second component is just 2y, so 2t squared. So taking this dot product, we are going to end up with an integral, and not 0 to 1, from 1 to 2, like we wrote up here, of this dot product. So 1 times 2t sine t squared, which is just going to be 2t sine t squared, plus 4t cubed dt. Integrating this thing, we are just going to get negative cosine of t squared plus t to the fourth on 1 to 2. Here we're going to get 16 minus cosine of 4, and here we're going to get 1 minus cosine of 1. So overall, our answer is going to be 15 minus cosine of 4 plus cosine of 1. And that is our answer choice here. It's choice D. Let's let r of t equal cosine of t, comma sine of t, comma t for t between 0 and pi, and our parametrization of the curve, let that be the parametrization of the curve C. And okay, this is important. F is a conservative vector field where f is the gradient of some potential function f, with that potential function being y cubed plus 2xz. And then we're looking for this line integral. So this was labeled as a line integrals question because I labeled it as a line integrals question during the second exam kind of studying cycle. But really, now we know that we can solve this with the fundamental theorem of line integrals, which tells us that if we have some potential function f, which we do right here, then instead of computing f dot dr, we can evaluate that potential function, which in this case is y cubed plus 2xz, on the starting position of, well, the ordered pair that is the starting value for our curve and our ending value, just like we would evaluate an integral, and we will get the value of this line integral f dot dr. And that's because this is a conservative vector field over here, it is path independent. So it doesn't matter what this curve C is at all, we will always get the same value as long as we start and begin. As long as we start and end at the same value. So all we have to do here is figure out what x, y, and z values t is equal to 0 and t is equal to pi correspond to. So let's see, r of 0 is going to be cosine of 0, which is 1, sine of 0, which is 0, and 0 for t, which is 0. Whereas r of pi is going to give us negative 1, 0, pi. So we can plug these guys in. Our ending point is negative 1, 0, pi, and our starting point is 1, 0, 0. So evaluating this end bit is going to turn into negative 2 pi, and over here we are going to get, well, let's see, We have a y here, y is equal to 0, and also z is equal to 0, so this whole thing's 0, and our answer is negative 2 pi. Let C be the oriented curve described by the intersection of this parabola and y equals 0 from that ordered pair to that ordered pair. So let's see. One thing to think about is whether or not this thing is whether this thing is a conservative vector field. And you can see right off the bat that it definitely is not. If we have an e to the x here, if we were taking a gradient to get this function here, that e to the x should also show up in our x component. So there's no way that this thing is that it is a conservative vector field. So let's see, what can we do? Well, we can parametrize things. So we see that r of t, we can make r of t as, last time that we saw this parametrization, it was really y equals x squared, and we know that when we see that, we set x equal to t and y equal to t squared. Well, we can do a variant of that in this case, where x is equal to t, z is equal to t squared, and, well, they're giving us this, y is equal to 0. So moving on from that, we have r prime of t, which is going to be 1, 0, 2t, and f of r of t, which will be, well, 3x squared is going to be 3t squared. E to the negative xy, well, y is 0, so that whole thing's 0, and then 1 is just 1. So taking our dot product, we are going to be left with the integral. Okay, what are our bounds on integration? We set t equal to x, and we see that x runs from negative 1 to 1, so those are our bounds. Negative 1 to 1 of 3t squared plus 2t dt, and evaluating t cubed plus t squared on negative 1 to 1. Here we are going to get 2, and down here we will get negative 1 plus 1, which is 0, and so our answer is 2. Let's evaluate this line integral where the curve C is parametrized by r of t, given here for t between 0 and 1. Well, this is a different kind of line integral than we've seen before. It's a line integral ds. We know that we can turn this into a more normal kind of line integral dr with the square root of rx squared plus ry squared plus rz squared, where rx, ry, and rz are the partial derivatives of, well, I should be specific. They're the derivatives of the x component, the y component, and the z component of r of t, and you'll see what I mean in a second, because we can find these just from finding r prime of t, which is going to be 1, 2t, 0. So now we can take our parametrization here, our r of t that we're given, plug it into this thing, and we will have our answer. Well, we'll have our integral that we can solve. We see that t runs between 0 and 1 of 12x, so 12t. Cosine z, well, z is 0, and cosine of 0 is 1, so times 1 multiplied by, let's see, this is going to be this guy is going to be this guy, and this guy is going to be this guy. So our square root is going to be 1 squared plus 2t squared plus 0 squared dt. So our integral can be simplified down to the integral from 0 to 1 of 12t times the square root of 1 plus 4t squared dt, which we can do some nice u substitution on in order to solve. We can set u equal to 4t squared, du to t dt, and this will turn our integral into the integral from 0 to 4 of, let's see, what's 12 over 8? That's it's that time of night. 12 over 8 is going to be 6 over 4, so 3 halves. 3 halves square root of 1 plus u du, which we can integrate pretty easily because 3 halves multiplied by 2/3 u plus 1 to the 3 halves on 0 to 4. This whole thing is just going to be 1 out here, and we will get 5 to the 3 halves, and over here we're going to get 1. So 5 to the 3 halves minus 1 is our answer. Okay, here we have another line integral in the form ds. So we know that we're going to need a parametrization for this, and we are given a line segment to parametrize. So we see that, x can be equal to 1 plus 2t, because we kind of always want to set it up so 0 is less than or equal to t, which is less than or equal to 1. And in this case, we see that this works out fine, because we want, when t is equal to 0, we want our value of x to be 1, and we'd like to add 2 as we go up in t. And really, you can parametrize this any way you want, as long as it works, as long as it is this line segment, you'll be fine. Y is going to be equal to 1 plus t, and z is equal to 1 plus 2t. And so that lets us form our r of t, which is just these components smacked together. 1 plus 2t, 1 plus t, 1 plus 2t, which gives us our r prime of t of 2, 1, 2. So we know that we can replace this ds up here with the square root of these components squared from our r prime of t. So that's going to be 4 plus 4 plus 1, or just the square root of 9, which goes down to 3. And that lets us turn this into an integral dt. And so we can set up our integral. We said that t runs from 0 to 1 of x, which is just 1 plus 2t plus 2y, so plus 2 plus 2t, plus z, which is just plus 1 plus 2t. And all of that is multiplied by 3. So this is looking a little sloppy over here, so let's figure this out. 3 times the integral from 0 to 1 of 1, 2, 3, 4 plus 2, 4, 6. So that's going to give us 12t plus 9t squared on 0 to 1, and that's going to give us 21. Let's evaluate f dot dr, where f is xyi minus yj, and c, our curve c, is given by this parametrization here, with t between 0 and 1. So, same thing as usual. Let's find our r prime, that's an f, whoops. Let's find our r prime of t, that's just going to give us 1, comma, 2t. And it's important to note, when they give you these in terms of ij and k, it's very easy to misread and think that they're just going ij, when sometimes they go ik, and you just miss that there's a whole, that there's a missing value that they didn't show you in there, which is 0. So now let's find our f of r of t. Well, our I component is just going to be xy, which will give us, which will give us t cubed, and our j component is negative y, which will give us negative t squared. So now taking this dot product, and I really don't set this up well for myself, putting them way over here, but we'll be left with the integral from 0 to 1 of t cubed minus 2t cubed dt, which will give us the integral of negative t cubed dt, which is negative 1/4 t to the 4th on 0 to 1, and that gives us our answer of negative 1/4. Let's let f equal to this, and we're looking for the line integral of f dot dr of this from 0 to pi over 2. So same old, it kind of gets old after a while. R prime of t is going to be negative sine of t and 2 cosine of t. And f of r of t, well, that's just going to be 2xy. So 4 cosine t sine t, comma, x squared, which will be cosine squared t, plus 4y cubed, which will be plus 8 sine cubed t. And okay, so you get to this point in the question, and you're starting to question whether this is a good use of your time, because this integral, while it's probably doable, is going to be a real pain and definitely a waste of time. And if they give you something like this on the final, well, really, if you ever see something like this that looks overly disgusting, the magical words of conservative vector field or fundamental theorem of line integrals should come into your head. Because if we take a look at our I and j components, if we know that these are if we have a hunch that these are the gradient components of some overall function, some potential function that they're hiding from us, we can try to figure out what that potential function is. And the way I kind of do this is take some antiderivatives here. Here we're going to do it with respect to x. Here we're going to do it with respect to y. So up here we are going to get x squared y comma, plus x squared. And over here we'll get x squared y plus y to the fourth. And this is great because we see some overlap here. So these came from the same source, so we only count them once. And we are left with our potential function f as being equal to, well, it's not a vector, it's a scalar, x squared y plus x squared plus y to the fourth. And that's awesome, and you can go back on yourself and check. If you take the gradient of this, you will end up with exactly what is written up here. And so that's a great confirmation that we've gone down the right route. And now all we have to do is evaluate this at our starting and ending values of our curve, and we can pull those x and y values right out of here. So for t is equal to 0, we're going to get cosine of 0, so 1, and this 2 times the sine of 0, which is just 0. And then for r of pi over 2, we will get 0 and 1. So we're ending at 0, 1. We're starting at 1, 0. We can evaluate this and we'll get our answer out. So anything with an x in it's going to be 0, so this whole thing is 1. And over here, anything with a y in it's going to be 0, so this whole thing is 1. Oh, okay. Quick little mistake over here. Pi over 2, 2 sine of pi over 2. That's going to give us 2 over here. So this is 0, 2, and so this is going to give us 16, and our answer is 15. Whoops, scared me for a second. Let's compute this line integral, and we see that it's in the form ds. So we know that when we have ds, we need to find the magnitude of our r prime of t, and that will let us replace it with a dt. So r prime of t is going to be negative sine t, cosine t, 1, and we can find the magnitude of this. This is just going to be sine squared plus cosine squared plus 1, so that's going to be root 2. And now all we have to do is set up this integral. We have the integral of z. Well, what's z in terms of r of t? That's just going to be t. So t times root 2 from 0 to 1 dt. That'll just be t squared over 2 root 2 on 0 to 1, which is just root 2 over 2. Let's evaluate this integral right here. Really, we can express this as f dot dr because all we have to do is take an r prime of t, which will be 1, 3t squared, 2t, and substitute this in for dx, this for dy, and this for dz, and plug these in for our x, y, and z values up here. So we have the integral from 0 to 1 of 4y, so 4t cubed dx, which is just 1. And then we're adding 5z, so 5t squared multiplied by 3t squared. And then we have 3x dz, which is going to be 3t, and dz is 2t, and all of that dt. We can simplify this down to the integral from 0 to 1 of 4t cubed plus 15t to the 4th plus 6t squared dt, and all of this will integrate to t to the 4th plus 3t to the 5th plus 2t, not to the 6th, to the 3rd from 0 to 1, and that's just going to give us 6. Okay, very, very big, scary line integral, and if you forget, if the fundamental theorem of line integrals doesn't pop into your head when you see something this disgusting, especially given the trig that they try to make you substitute in, definitely go check out. I did a whole thing on the fundamental theorem of line integrals, and you can really get it smashed into your skull some more, because it's a very good thing to have up your sleeve because it saves a hell of a lot of time. So we can go through this. We have a really good hunch that this is going to be a fundamental theorem of line integrals question, and as it turns out it is, but we still have to check. So let's take our antiderivatives. We will find that our first component will be x squared y cubed plus 2x z squared. Our second component will be x squared y cubed plus 3y z squared. And then what we would hope to happen, given that we've already found a term with x and z in it, and we've already found a term with y and z in it, we would hope, and it would confirm things for us if when we integrate these guys, or take the antiderivative of these guys, that we do in fact get overlap with these two. So, and we do, because we will get 2x z squared plus 3y z squared. And that those are identical to the two that we've already found. And so we have, in total, 3 sets of overlap. We have this guy matching this guy matching this guy, and this guy matching this guy. So we only count each of these once, and our potential function f is x squared y cubed plus 2x z squared plus 3y z squared. And now all we need to do is figure out what these t values for r of t correspond to in terms of x, y, and z. Well, r of 0 is going to be 0, 0, 0, and r of 1 will give us, well, let's see, this is going to be 1 times the cosine of pi, so -1. This will give us the sine of pi, which is 0, and 1 cubed, which is 1. So now we're evaluating this with 0, 0, 0 down here, and -1, 0, 1 up here. And we are going to get, well, anything with a y up here is going to be equal to 0. And so this whole thing 0, this whole thing 0, and we are left with -2 up there. And then 0, 0, 0, everything's going to be 0. So our answer is -2. Let's find the work done by this force moving an object along the semicircle with y greater than or equal to 0. So that's going to be our upper semicircle here, moving in the counterclockwise direction from 1, 0 to negative 1, 0. So we know that we can parametrize this as r of t is equal to cosine t sine t, where 0 is less than or equal to t, which is less than or equal to pi. And finally, r prime of t is going to give us negative sine t cosine t. And sorry, that wasn't finally. I wish it was finally, because f of r of t will give us negative y, where negative y is going to be negative sine t and x, so cosine t. Now, since we know that whenever they say find the work done by this force, really what we're doing is a line integral over c of f dot dr. This is what we've already been working towards, but it's good to get that terminology kind of connected in your head. All we have to do is take our f dot r prime over here, and we will get cosine squared t plus sine squared t. So really, we're just integrating 1 dt over the bounds 0 to pi, and this will just give us pi. Okay, let's see. Ooh, 3 questions left. I thought it was only 1. Let's evaluate this line integral where c is the curve parametrized by this whole thing. We see that it's a line integral ds, so we're going to need the magnitude of r prime of t. We can find r prime of t as a good start to this question. That's going to give us negative 2 sine 2t, 1, 2 cosine 2t. And so the magnitude of this is going to be 4 sine squared 2t plus 1 plus 4 cosine squared 2t. And this will work out to root 5. So now all we have left to do is take our integral from 0 to pi, like they say our bounds are up here, of, well, sick root. I don't know where root 3 came from. Whoops. Root 5 times y in terms of r of t, which is just going to be t, 5t dt. That'll be t squared times root 5 over 2 on 0 to pi, which will give us pi squared root 5 over 2. Pi squared root 5 over 2. There we go. Okay, evaluating the line integral xy dx minus y squared dy, where c is this line segment. Well, we can parametrize this as x equals 2t, y equals 6t, from 0 is less than or equal to t is less than or equal to 1. And doing this in a slightly different way, maybe this is a way that you guys like better, at least for some of you, because when we're dealing in xy dx and dy up here, it's sometimes easier to stay away from any r of anything. You can just do dx is 2, dy is 6, and maybe that's a little bit easier to see because now we can just integrate from 0 to 1 of xy, so that'll be 12t squared dx. Well, dx is just the derivative of that, so 2. And then we're subtracting y squared dy, which will be 6 times 6t quantity squared dt. So this will be 216 t squared, and 24 minus 216 is going to give us an integral from 0 to 1 of negative 192 t squared dt. And this will give us, well, we take 3, and well, if we take 192 and divide it by 3, we are going to get 64. And so this will be negative 64 t cubed on 0 to 1, which is just negative 64. Okay, last question. Let's evaluate this line integral. It's in the form of ds, so we're going to have to find our dx and dy. This will be t squared, whoops, t squared, and this will be t cubed. And so our magnitude of this, of these two, is going to be t to the fourth plus t to the sixth. And that's looking a little messy, but let's see what we can do with that. We know that we can multiply, we can take this tt and replace our ds that we had there before with this thing. But before we do that, let's figure out what the rest of our integral is going to look like. We are integrating from 1 to 2 of 9x, so 3t cubed over y, which is going to be t to the fourth over 4. We can rearrange this, and we will get 12 over t ds. And we said a second ago we can replace this ds with root t to the fourth plus t to the sixth dt. And this still looks pretty ugly, but it's actually okay because we can take this thing right here, factor a t to the fourth out of everything, and this thing will be equal to t squared root 1 plus t squared. And that's still looking a little ugly, but let's see what happens when we actually do that up here. We will get the integral from 1 to 2 of 12 t squared over t root 1 plus t squared dt. And this will just simplify down to 12t. Now we can do some u substitution. U is equal to 2. Oh my god. Oh, I'm so tired already. I'm sorry. So many tiny little mistakes everywhere. U is equal to t squared. Du is 2t dt. And so we can set our integral back up as the integral from 1 to 4 of 6 root 1 plus u du, which will be 2/3 times 6 times the quantity 1 plus u to the 3/2, evaluated on 1 to 4. This is just going to give us 4 out here. So we get 4 times 5 to the 3/2. And down here we get 4 times 2 to the 3/2. So our answer is answer choice B. And we're done. That felt very sloppy on my end. I haven't practiced these in a while. But it's very good practice for me, and so this is great. Also, I did skip this question. I even went back and looked at my own video that I made, and then remembered as I was watching that this was the one video that one of the only questions that I was like, yeah, I actually don't know how to do this. So still, if you guys, I don't know, it's a nice little challenge. If you want to try this question, feel free to send me the solution, and that makes no sense. I won't feel free. I will definitely upload it and give you credit, because I would really like to get this thing out of the way. I just working through the few parametrizations. I'm not too happy about that. But I hope this whole thing was helpful.